Hello, my name is Yago, and today we're starting the discussion about complex numbers. The idea of this new playlist is for us to study basic properties of complex numbers, but my focus after we see those properties is to see applications of them. Okay, applications on, for example, partial fractions and phasor analysis, but we do not want, or we will not get into complex analysis, which is the part of complex functions, right? We're not going to get to this. We're going to see only basic definitions of the complex numbers, and also we're going to define them as a vector space, and understand vector spaces of complexes or over the complex set. Okay. I brought here these guys were very important mathematicians who contributed to the understanding of complex numbers as they are today, like Abraham Demoivre, Leonard Euler, René Descartes, Friedrich Gauss, Giordano. All these guys contributed, and they made it possible for us to study complex numbers with the high degree of detail that we have today with all the rules and everything. Okay, we intend to follow the contents as in this book over here. Okay, this book is Complex Variables and Applications by James Ward Brown and Roel Churchill. It's a very famous book, and I think it's very good for this part of for the starting discussion about complex numbers because it starts defining all the basic properties, and we're gonna follow through with it. But also, intend to add some things because as I was studying this topic for the first time, I had some questions, especially about the definitions of a complex number as a vector. And to do that, we're going to use another book, okay, which is uh, this book over here on linear algebra, which will have some basic definitions that are very important to understand why the complex set, the complex number set, can be considered a vector space. Okay, I already selected some parts of this book that are going to be very important. The definitions of number fields and linear spaces, they're going to be very essential for us to understand the complex numbers. And we're going to see this in these videos. Okay, another thing that I wanted to show after we see those basic properties is some applications that are very useful in electrical engineering, for example, which is the use of phasors or phasor analysis. And this is very important because it's very useful to use these complex numbers to simplify trigonometric operations. Like when we use trigonometric identities, instead of using them, we can use the representation in an exponential form of a complex number. And this facilitates a lot operating with trigonometric functions. Okay. Another thing that we're going to see is partial fractions. I think we're going to see this in the beginning, in the next videos. How to use the limit method for partial fractions. I know that it's kind of not necessarily related to complex numbers, but there's some involvement of complex number properties, and we're going to see the four different cases of partial fractions. And this is going to be important because I intend to discuss Laplace transform in the future. Now that we have seen an overview of, we can start thinking about the complex number set. But firstly, let's understand what is an imaginary number, right? An imaginary number. And the history of this, I'm not gonna get really into here, but you can find it in detail in a Wikipedia page. And I really like the way the Wikipedia page organized the history of the imaginary numbers, starting with um, all the works in algebra through history that took us to where we stand in the complex analysis. Okay, it talks about the fundamental theorem of algebra, Cardano, as we mentioned in the first video. And it goes through the Descartes contributions, Linus Euler's contribution. So it's a very interesting text on the history here, and you guys can click on the on the names and on all the references, and they are really good. I really liked it, but in short, okay, the complex numbers are very important because they allow us to solve problems that didn't have solutions before. Okay, so basic algebraic problems that didn't have solutions we can now solve by considering this imaginary number. Okay, and but at first glance, of course, this wasn't well accepted. Just like when you think about numbers in the beginning, zero wasn't such a thing. Like zero wasn't a number, and it couldn't be considered a number. There was only the natural set. Okay, only numbers like one, two, three, four, five, and these were numbers that could be counted like objects. Like these were considered to be real things. But then after, when we had operations like subtraction, we needed to define a new kind of number, which was the negative numbers. So the negative numbers, they weren't considered to be a thing before, but now they are. And of course, irrational numbers and other kinds of numbers that all are in the real set, as we know today. Uh, but then some problems uh, happen in nature, and of course, in algebra that didn't have solutions. And when you consider this, okay, when you consider this imaginary numbers and define this complex set, you find the solutions to those problems. So that's why this is important, okay? And to start our talks about the complex number set, we can define this set as a set C, for example, equals to, and it is formed by numbers of the form x plus yi, where x and y are real constants, okay, they are scalars, and of course I is equal to the square root of minus 1. Okay, so this is the definition of the set of complex numbers, and that is the definition of the complex numbers over the real numbers. And this thing here is the imaginary part of the complex numbers. Okay, and this thing is the real part of the complex numbers, and that's how we can consider uh, this set also as a field. Okay, so this is a field because it you can define basic operations with this. So the complex number set is a field. What is a field then? Okay, so the definition of a field. For the definition of a field, I'm going to use this book over here. It is the Georgi Shilov book. This is a definition of a number field. Okay, according to him, a number field, by a number field, we mean a set K of objects called numbers, which when subjected to the four arithmetic operation, again give elements of K. So what does that mean? If we get a complex number of the form z equals x1, for example, x1 plus y1i, and z2 equals x2 plus y2i, and we do the basic operations with these numbers, like a sum of these two numbers, or a product of these two numbers, this is going to be equal to times x2 plus y2i. A product of these two numbers will be real part product, okay, so it's going to be x1, x2, and then minus y1, y2, okay, because of the square here, plus um, y1, x2, plus x1, y2. All this, the imaginary part. You see that this product over here results in another complex number, just like the sum results in another complex number, just like the difference results or a subtraction results in another complex number, which means that any of the four operations, and even division that we're going to see a little bit later, they're all defined within the complex number set, which means this is a field. Okay, so this is a number system, and it is just another type of number. Okay, the real numbers are just defined. You can imagine the real numbers as a complex number like the number z with only the real part. So this is a real number. The complex number will be zero. The imaginary part will be zero. Okay, so this is a complex number. All right, with only the zero, the imaginary part multiplied by zero. So um, well, so it's very important to define the complex numbers as a field because it can also be, or it can also be a vector space over the R set. Okay, why can it be a vector space? Because it has the properties of vector spaces. We shown here that we can add elements of the complex numbers and still obtain a complex number. And we also can define another operation, which is the scalar multiplication. Okay, so if you get a number z1, for example, the one that we define here, multiply it by a scalar alpha, we obtain alpha x1 plus alpha y1 I. And this is still a complex number. So it is defined under scalar multiplication. And therefore, it is defined under the sum and the scalar multiplication. That makes the complex number set also a vector space. So it is a field and it is a vector space, okay? And why is that important? Because a complex number itself can be thought of as a vector. And a basis for this vector space would be 1 and I. And what is a basis for, if you didn't see linear algebra yet? A basis is an a basic element that can basically span a vector space. And by span, it can create, right? It can create a vector space. And if we can get any complex number z, for example, as a linear combination of 1 plus y times I. Okay, so this is a basis. A basis for R2, for example, if we imagine the real vector space R2, okay, a basis for R2 would be, using this basis here to represent basis, would be, for example, the 1, 0 and 0, 1. Okay, so we can define any vector, if we think of a vector omega from R2, okay, we can have a vector omega described as a linear combination, for example, of this basis vectors over here. And for these two constants, a and b being real numbers, being scalars, and this is very interesting because this basis vectors over here, they span any vector from R2. So what is happening here is this basis over here formed by 1 and I, which makes it a two-dimensional vector space. This makes a two-dimensional vector space, okay? Um, this is very interesting because with these two elements over here, we can span any complex number. And we can think now of complex numbers as vectors themselves, and that's going to be very useful. And we're going to see this in the next classes. And well, we just did this parallel over here with R2 because uh, they're both two-dimensional vector spaces. You can see a basis for uh, R2 and a basis for the complex number set. They're both two-dimensional. So that makes it very interesting to compare these two sets, okay? These two vector spaces. And It's useful to consider the complex number vector spaces because we can do a vector representation of the complex numbers. And we can also do a polar representation of the complex numbers. And we're going to see this in the next couple of videos.